later, you can order this book and then enjoy it for the next few years.
It makes a good doorstop as well. Excuse me. Okay. I want to talk about lattices in the sense of essentially the underlying graph of the lattice, the network. So here we have part of the infinite square lattice with nearest neighbour connections. I'm just going to draw the connections as bidirectional lines between them. And the symmetry group of the square lattice is essentially the D4, fix a point, you've then got dihedral group of order 8 of rotations and reflections, and then you've got the translations of the lattice. And that's the symmetry group of the whole lattice. It's a semi-direct product, and symmetry groups are going to be the main theme of this talk. You can have nearest and next nearest neighbour connections, you can have longer range connections, there are all sorts of different ways of converting the points of a lattice into a graph. You've still got the same symmetry group when you increase the range of connections. And of course also we have hexagonal lattice. I'm going to talk about that a little bit. Again, you can have nearest neighbour connections, nearest and next nearest neighbour connections, longer range connections, and the symmetry group is very similar, but now there's a dihedral group of order 12 at the point of the lattice. Okay, now what I want to talk about are what are called balance colorings on networks, and these are to do with the possibility of having a dynamical system attached to each node, and it's essentially the same system, coupled together according to the connections of the graph, and a balanced coloring actually gives you synchrony between certain nodes. So this example will show you. So on the left, here's a little 5-node network. It has trivial symmetry. You can check that. If you permute the nodes in any way except the identity, you can't preserve the arrows. And on the right is a coloring of the nodes. There's 2 yellow ones, 2 magenta ones, 1 green one. And this is a balanced coloring, which means that if you choose 2 nodes of the same colour, let's say 1 and 3, which are both yellow, and look at their input nodes, they've got 1 green and 1 magenta, and that's true of both of them. So balanced colouring means nodes of the same colour have input sets which, if you permute correctly, match the colours. And there is a theorem essentially that says if you identify all the nodes of the same colour, that is giving you synchronous dynamics, everything reduces to, you collapse the network down to just 1 node per colour, and you copy the inputs. So let's do that with this one. So on the left is the 5-node network. On the right, I have node 1 yellow, node 2 is magenta, node 5 is green. And I have copied the inputs. If you look at any of the magenta nodes, they've got 1 yellow and 1 green. And you look at the magenta node in the quotient network, and that's got 1 yellow and 1 green. The associated with this is a synchrony subspace of the phase space of the whole system, in which coordinates of nodes with the same colour are equal. And the theorem is that you get a dynamically invariant subspace for any system of differential equations with the lattice structure, well, with the network structure, if and only if the colouring is balanced. So these things are fundamental. And balanced colorings give you quotient networks. Yeah.
If the arrows go both directions, mean they're inverses.
Okay, now these are unidirectional arrows.
What?
These are unidirectional arrows on this network. On the lattices, they're going to be bidirectional, which is essentially 1 arrow in each direction. But for this network, the arrow is a directed network, directed graph. Yeah? So node 4 gets inputs from nodes 5 and 1, but node 1 does not get an input from node 4.
When it's a double arrow, are they inverses?
If double arrow, they are identical couplings in each direction. Yeah. Okay, if it was a double arrow between 1 and 4, you got it? If there was a double arrow between 1 and 4, then the equation for node 1 would involve node 4 at some point. The equation for node 4 would involve node 1 at the same point with the same function. Yeah?
I don't know what the arrows mean.
I'll show you some differential. I'll get to that in a minute. Yeah, don't worry about it. So here are some papers. Okay, now I'll start to answer Dennis's question. Associated with any directed network, you can write down a system of differential equations by putting, let's say, a variable at each node, x1 to x5. And if we look at the x1 equation, the dash there is the derivative. It's some function of the node itself and then the two nodes at the tail of input arrows. The bar over the top means it's symmetric in the two variables because the node doesn't know, it's just got two inputs. The assumption is it doesn't know where they come from, it just knows what is being sent to them. So the general set of admissible differential equations, these are the differential equations whose structure is, it essentially respects the structure of the network. The coupling in the differential equations corresponds to the arrows in the network.
F is the same everywhere.
F is the same everywhere because we assume all of these nodes have the same dynamics and all of the couplings are the same. There's a more general version which I'm not going to subject you to with different kinds of nodes and different kinds of arrows. And then you get Fs and Gs and all sorts of things. Yeah. So if you look at how the colouring goes, I've coloured the relevant variables, and if you assume that variables of the same colour are equal, we get 5 equations, but there's 2 different equations for x1, but if you look at them, they're the same equation. So you get a consistent set of 3 equations, which is actually the admissible differential equations for the quotient network. And this is basically a theorem. Furthermore, every admissible equation for the quotient is obtained in this way. So the ODEs on the big network restrict to the small one, to the quotient, and any admissible ODE on the quotient lifts to one on the original network. And it's the balanced colouring that tells you that happens. And the admissible equations are essentially the class of equations that if you were modelling some physical system or biological system with a network of this kind, it would have to, the equations would have to have that structure. That's what the network's telling you. The biology or physics might tell you what F is, and so on. Okay. So dynamics on the quotient lifts. Nodes of the same colour then are synchronous. You're looking at synchrony patterns. But the point is that the symmetries of the original 5-node network, which are trivial, do not explain the patterns. It's a fairly straightforward theorem to show that if you have a group of symmetries acting on the network, the orbits of that group on the nodes give you a balanced colouring. But here we've got a balanced colouring that does not arise from the symmetry group. Although the quotient network has dihedral group D3 symmetry. So the original network has no symmetry, the quotient has more. Okay. So you can use the symmetries to predict certain synchrony patterns which give you these invariant subspaces, and therefore you will expect to see those patterns in the dynamics. And if we have, for example, a ring of 6 nodes with bidirectional coupling, symmetry group D6, dihedral group, there are actually 7 balanced colourings that come from symmetries. This shows 6 of them. If we take the whole group and look at the orbits of that is all the nodes. So they are all 6 nodes are synchronous. If you looked at the dynamics, they would all have exactly the same time series. Then the other patterns here come from different subgroups of D6. And finally, when you get to the identity group, which I didn't bother to put up, you have 6 different colors. Each node is just synchronous with itself and not with anything else. Yeah, and you can figure out the subgroups from what preserves the colors. So if we go back to our 5-node network and its colorings, down on the quotient, which is a D3 network, there are certain standard synchrony patterns you can observe. So one of them is that one of the nodes does its own thing and the other 2 are synchronized with each other. So maybe node 1 just has some waveform, but nodes 2 and 5 have the same waveform as each other. Another pattern is node 1 could oscillate periodically with some pattern. Nodes 2 and 5 could oscillate with the same waveform but half a period out of phase with each other. This forces node 1 to actually have twice the frequency. And on the quotient network, that kind of structure makes perfect sense, and there are general theorems about existence of these patterns. But when you lift back up to the 5-node network, those patterns lift up as well. But now instead of, let's look at, so one of the things you see on the quotient network is a rotating wave in which successive nodes round the triangle are 1/3 of a period out of phase with each other. So you've got something like a sine curve, the whole thing displaced 1/3 of a period, the whole thing displaced 2/3 of a period. You lift that up and you get the same 3 waveforms, but now 2 of the nodes in the 5-node network are on one of these, another 2 are 1/3 of a period different, and the final one is 2/3 of a period different. And that kind of setup. You can even lift chaotic dynamics. So you get some sort of chaotic pattern on the quotient, lift it up, and you will see here there are 2 possibilities, that 3 of the nodes are doing the same thing and the other 2 are something different, or all 5 of them are doing the same thing but chaotically. Okay. Now, a long time ago, Marty and Yang Wang looked at balanced colorings on the nearest neighbor square lattice. They classified them all. So we're now getting towards the lattices, and there are these 8, and then there are these as well. And some of these are quite surprising. Most of the ones I've shown you here come from subgroups of the symmetry group of the lattice, and you're just looking at the orbits of that subgroup. 2 colors only. But some of them, particularly, let's take this one up there. I suppose I can use this. Where's it gone? I don't know how to control this. It starts in the middle, and then it comes up. There we go. That one. It's got a lot of structure geometrically, but that is not the colouring from orbits of a subgroup of the symmetry group of the lattice. Roughly speaking, the cells in the corners of the big squares are not in the same orbit as the cells in the middle of the sides of the big squares.
What's the definition of balanced coloring?
Balanced colouring, every node of a given colour is connected to a set of nodes, and it's the same set of colours that you see. So look at this bottom one left that I was talking about. If you look at any black square there, it's got 3 white neighbours. Doesn't matter which one it's got 2 black and 2 white neighbours. So the a black square in the, let's see if I can persuade this thing to come over here. Here we go. These black squares, the 4 of them, each one of them has 2 white neighbours, just its nearest neighbour, so it's only vertical and horizontal. And then underneath it and across to the right of it are 2 black. So each black has 2 black and 2 white. But they're not necessarily arranged in the same order around, because the network structure doesn't actually recognise that order. Similarly, each white square has 2 black and 2 white neighbours. Yeah? So that's balanced. If somewhere there was a black square that had 3 white neighbours and 1 black, and somewhere else was one that didn't have those numbers, it would not be a balanced colouring. So if you colour them at random, for example, it's not going to be balanced. And similarly, Marty and co-workers classified all the balanced colourings of the nearest neighbour and next nearest neighbour hexagonal lattice. And the same kind of thing happens. There's a whole catalogue of these balanced colourings. Now, each of those correspond, if we had a dynamical system with that lattice structure, each of those colourings would give you patterns in which all the black squares are synchronised, all the white squares are synchronised. And it might be a periodic pattern, or it might be a steady state pattern, it could be chaotic dynamics. And for, yeah?
Can I just ask about the square thing going back? I was thinking about the balance, you're giving the definition.
Yeah.
So I had another example, I want to ask if it's also balanced.
Yeah, okay, take.
So if I start with 4 adjacent squares, like in your left picture,
Yeah.
and then I have a white path around it, and then a black path around that, and then a white path around that, and so it's concentric squares expanding. That's also balanced?
That one is actually balanced. It's, yeah, there's something I'm sliding over here, which I'll come to. Some of these patterns you can actually shift diagonal. You can shift black. If you have a diagonal that goes black, white, black, white, black, white, you can slide that along one and still get a balanced pattern. And I'll come to that in a moment. And the pattern you've just described arises from one of these by that process carried out infinitely many times. So we don't list it. Yeah, I mean, there's a similar one here in the hexagons. Yep. Down. Yeah, that's right. Okay. So, this is just warm-up. So, there is a difference between orbit colorings, which is take a subgroup of the symmetry group, look at its orbits, color everything in the same orbit, the same color. And the ones along the top here are all orbit colorings. For example, the first one, if you take the whole pattern and translate one step to the right, and then take the subgroup that generates, and then also you take translation by 2 steps vertically, you would generate the pattern of stripes. And for each of these you can find the relevant subgroup that generates it. But the bottom 2 are not generated by a subgroup. We call them exotic. They arise for combinatorial reasons rather than for symmetry reasons. And now we come to this idea of swapping on diagonals. As an example, if you take this colouring on the left, which is an orbit colouring, there's a suitable subgroup that will generate that colouring, and you look at some of those, the diagonals that go from bottom left to top right alternate black, white, black, white, black, white. And if you slide any one of those one step up, the colouring remains balanced, but now you're destroying the symmetry. So you can get things like stuff over on the right. If you're discretizing some PDE using nearest neighbour lattice discretizations, this sort of phenomenon can create a whole pile of artifacts that you would not really want to have. You can see how this happens by just looking at one of these diagonals and moving everything up. Basically what happens is that 2 neighbours of opposite colours change to 2 neighbours of the other complementary colour. So you've still got 2 black, 2 white. If you move up one, you swap a black with a white and a white with a black. But there's another way to think of this, which is getting towards the point of this talk, main point. Think of the subgroup that shifts everything 2 steps diagonally, but don't worry about translations in the horizontal direction. And look at the orbit colouring for that group. Here's a little bit of it. So as you go up a diagonal, 2 different colours alternate, but each diagonal has its own pair of colours. Okay? And then you ask, what's the quotient network for that colouring? So I'm going to take an orbit colouring from a nice simple straightforward subgroup and look at the quotient. And the answer is the quotient looks like this guy on the right. Now each node in one of the columns of 2 is connected to both neighbours on either side. So if I flip that column upside down, it's still connected to both neighbours on either side. So the colouring remains balanced. And if I lift that back, what I've done is translate that diagonal 1 step. So we can see, we can kind of relate the patterns you get by shifting along diagonals to flips on what's actually a wreath product group. I think this is what the, well, it's very close to what group theory is called the lamplighter group. You have a street full of lights and somebody comes along and lights random ones on it. Here they come along and flip random ones along it. So the group theoretic explanation is that there is an orbit colouring on the original network, which when you take the quotient has a whole pile of extra symmetries that weren't there in the original network. And if you then take orbit colourings for those subgroups of that, you can lift back to balanced colourings of the original. So there's a kind of 2-step process where symmetries create patterns. So you can explain some of the exotic patterns on one network as orbit patterns on the quotient network. And that's essentially pictures of what I've just told you. So we've got the quotient network structure. We pick an orbit pattern on that from translating sideways, and then we randomly flip. And that's an orbit pattern as well for a suitable subgroup. So the moral of the tale is that the symmetries of a quotient network can differ significantly from the original network. There can be more, there can be less, there can just be different symmetry. And the network symmetries constrain the dynamics and the bifurcations. And I will eventually get round to that. So that's my way of a warm-up. And the central part of the talk is about what happens if you play that game looking for doubly periodic patterns. So I take a square lattice, nearest neighbour connections, and I'm looking for balanced colourings which are periodic in 2 directions, like wallpaper. Okay? So here we have a sublattice. So red is the origin. Magenta are translates of the origin by some sublattice, which is given by this green parallelogram. That's the period parallelogram. But I can convert that. That's a fundamental domain for that subgroup. In other words, translates of that domain tile the plane. But I can convert it into a rectangular tile by chopping pieces off and shifting them around. And when you do this, the structures of the tiling you get are given by 3 numerical parameters. So your basic rectangle is A by B units, and you tile horizontally, just fitting them together like a line of bricks in a wall. But when you move up to the next layer, you translate sideways by C. So we have triples A, B, C, which define the sublattice that we're interested in. And with Denis Gokadin, who was a he was actually an MSc student at Warwick at the time, and he was a psychologist by background. But he got very interested in this stuff, and he's very bright. And we wondered what the symmetry groups of quotient networks would be for this kind of subgroup structure. So let me tell you the theorem. Okay. The symmetry groups you would expect, what we're doing is that the quotient network is actually converting that rectangle to a torus. It's a discrete torus. It's got A units round one way, B units round the other way. It inherits the symmetries of the original square lattice in general terms. It won't inherit the rotations, but the translational symmetries will certainly be there, and some of the rotations might still be there. And usually that's all you get. So usually the symmetry group of that quotient torus is predictable from a suitable subgroup of the symmetry group of the original torus. And those are the ones where nothing really interesting happens. But then there are exceptions. And there are 2 infinite families of exceptions and 5 individual exceptions. And I'll show you those in a moment. Okay, but look at this table, it's weird. So for certain values of those 3 parameters, 512, 612, 813, 1013, 440, your automorphism group is not what you expect. For one of them it's a symmetric group, for one it's the full octahedral group. One, it's part of a family, it has 1,152 automorphisms, but it doesn't fit neatly into the infinite family that it's essentially a member of. One is S5 cross Z2, and one is the hyperoctahedral group, which is the symmetry group of the hypercube, 384 elements. And then there's 2 infinite families which have this sort of wreath product structure. I'm not going to prove that. The proof is a bit of a combinatorial scramble using various features of the graphs, but I will explain where some of these funny ones come from. So there's an S5 symmetry, the first one on the list. That's this tiling pattern. So your basic rectangle, if I can persuade, here we go. So blue, red, orange, yellow, green. That's a 5 by 1 rectangle. And then I displace that by 2 and copy it again. Okay, now, what's going on? That's not right. Yes, that's right. Yep. So, pick one of the nodes of this. Let's say, come here. Let's have that green one. What are its 4 nearest neighbours horizontally and vertically? 1 red, 1 blue, 1 orange, 1 yellow. Pick a yellow one. What are its 4 neighbours? 1 red, 1 blue, 1 green, 1 orange. Each one of them, its 4 neighbours are the other 4 colours, which means that the quotient network is this. It's, don't worry about the colouring for a minute. Go to the right-hand one. The quotient network is the complete graph on 5 nodes, which means it's got S5 symmetry, which means that any subgroup of that, take the fixed point space, it's a balanced colouring, which means, for example, you could make nodes 1 and 2 the same colour, and it would remain balanced. Now, that's not normally the case. You can't take a balanced colouring and identify certain colours and expect it to stay balanced, but in this case it does. So if you lifted that one up, you would get this colouring of the square lattice, which is not given by a symmetry subgroup of the symmetries of the square lattice, but it comes from a subgroup of the symmetries of the quotient. So now we've got 2 reds next to each other, but if you look at that, each red has a red neighbour, a green, a blue and a yellow. And that's true for all the reds. Each yellow one has 2 reds, a green and a blue, and that's true for every yellow one, and so on. So you generate exotic colorings from orbit colorings of exceptional quotients. Now this affects the bifurcations, and that's why in the dynamics of these things it's important. So back up in the big lattice, the kind of equations you would expect to have the lattice structure look like what I've written down here. That you have for each point CD in the lattice, coordinate C and D, you have x sub CD as the coordinate. And the derivative of that with respect to time is a fixed function f, could be any function but it's the same everywhere, of the variable for that node and the 4 variables for the 4 adjacent nodes. And because the 4 connections are identical, it's symmetric in all 4 of those adjacent nodes. Okay, and this looks basically like it's standard for the lattice. Now, if you do your lattice standard ODE theory for solutions with the lattice symmetry, you get certain kinds of bifurcations and certain possible stable states. But for the S5 quotient, there's a theorem that says all bifurcating states are locally unstable. So the stabilities of the bifurcating branches are different from what you would expect from the lattice symmetry. They're coming from the S5 symmetry instead. So it has significant effects on the dynamics. Here's an example again. If you take the 10 by 1 rectangle and displace it 3 places and draw the quotient network, it looks like the one I've drawn here. And if you look closely, you can see that that's 2 copies of the complete graph, and you flip upside down. So you've got S5 worth simultaneously permuting both ends, plus a flip, and that's why it's S5 cross Z2. And the most interesting one, which graph theorists know about, it won't be a surprise to graph theorists, is the 440, which is a 4x4 square, and you just tile like bathroom tiles, you don't translate. The quotient network for that is the edges of a hypercube. May not be obvious here, but there is an extra symmetry you would not expect from the square nature of this picture. So on the left-hand picture, I've got blue lines drawn vertically, red lines drawn horizontally. The other picture is the image of that under an automorphism of degree 3, of order 3, and it takes the red horizontal lines into the red squares that you see, and the blue vertical lines into the blue squares that are shown, and the red and the blue alternate. And you can sit down and check that that picture actually gives you a symmetry. For example, node 5 is connected to 4, 6, 1 and 9 on the left. Node 5 is connected to 4, 6, 1, yeah, the 6 around the back and 9. So the horizontal things wrap round, the vertical things wrap round. Yep. So you can check one by one that that's an automorphism. Where did it come from? Okay, it comes from this. You now recognize on the left, standard picture of a hypercube. You put a cube inside a bigger cube and you join everything up. So you can see various 4 cycles in there, but you can also see, okay, so there's obvious 4 cycles, which are faces of this cube or faces of the big cube. There. But there's also 4 cycles which go this way, come in diagonally. And if I were to slice this apart along that face and open it out, I would have a tube formed of 4 squares going that way and 4 squares going this way and wrapping round. So you're seeing, and then you could unwrap that and you would get the picture of the 4x4 lattice. So that's a picture of the quotient. Now if we look down the hypercube along a diagonal, that's the picture on the right, you see there is a 3-fold rotational symmetry. And that 3-fold rotational symmetry induces that transformation of the nodes. So that's where the hypercube is coming from.
What do the colors represent in that right hand?
Okay, the colours there are the orbits of this order 3 rotation. Yeah. So it fixes point on the diagonal and it rotates 120 degrees, everything else. If I were to lift that back to the original picture, I would have a balanced colouring of the 4x4 of the square lattice with a repeated tiling of 4x4 tiles. And you can play the same game for the hexagonal lattice, but now your basic tiles are parallelograms with 60-degree angles in them. You've got 3 parameters again to define the tiling. And the theorem is that the exotic cases are, again, 2 infinite families and 3 others. And one of them, the symmetry group, is the symmetric group on 7 elements. Z2 Reith S4, which is basically, anyway. Z2 Reith dihedral, that's one of these Reith product-like things where you can flip all sorts of possibilities. There's another similar one. And then 330, it turns out to be the symmetric group of degree 3, Reith, the symmetric group of degree 3, of order 1296. And let's look at the interesting one, which is the 713 tiling. So outlined in a wiggly red line is a repeating unit. It's not one of the parallelograms, it's actually hexagonal. And what you see there is in the middle of it is the black colour 1, and then surrounding it are 6 different colours. This, of course, is the famous 7 colouring of a torus. Yeah? A map drawn on a torus needs at least 7 colours in general to colour it. And this is coming up in this lattice structure, and the quotient is the complete graph on 7 nodes. Okay. And you can look at various of the patterns from that catalogue. You can see how they're built from a doubly periodic translation of parallelogram. You can look at the quotients, which I'm doing here, and then in this case you can see that you could independently act on any one of the 3 connected components of the quotient. So again, you're seeing extra symmetries that you would not have expected. And there's a repetition of the relevant references, and basically, and there are some more. Baldi and Wigner came up with a different way of thinking about this stuff in 2002, and DeVille and Lerman have done some work independently as well. And instead of balanced colorings, they work with graph vibrations, which are essentially, instead of the coloring giving you a quotient, you look at the map from the original network to the quotient given by identifying the colors, and that's a graph vibration. And you can describe the whole topic in that language. So I wanted to acknowledge the work. So the top two first paper is the one that classifies the two color patterns, and the next ones are what I was talking about just now, and then this is other related work. Okay, thank you.
Thank you very much. Are there any questions or comments? Please.
I was curious about motivation when you have the linked systems for like a finite graph. I can imagine examples where that might be like a predator-prey system where you have several species.
Yep.
And the arrows indicate who's eating whom. But for like the infinite example, what are the like motivating examples? Or is there maybe some magnetism or atoms?
Yeah, there's a lot of physics ones which are there's a lot of lattice models that physicists use. It's kind of the continuous analog of coupled map lattices. So coupled map lattice is the same game but played with discrete dynamics, time 1, 2, 3, 4, 5, instead of continuous. So it would be iterating a function rather than solving an ODE. Biologically, a certain amount of, if you've got skin or some two-dimensional piece of tissue, lots of cells sending signals to each other, and they mostly send signals to their nearest neighbours which are in contact with them, then you could idealize that to an infinite lattice with some sort of, I mean, there's some interesting technical issues about ODEs on infinite lattices, but they're locally finite with nearest neighbor connections.
Two-dimensional lattices, is that because of the slides? It's easier to draw on a board, or is there something
There are some analogous phenomena in 3 dimensions, and probably more, but it's very hard to draw. Absolutely. And the basic ideas already show up in this 2-dimensional case. I have no idea what the analogous set of theorems for 3 dimensions would be. You would guess again that there are some funny exceptions and infinite families. And a lot of it will be trivial.
Part about like the solutions breaking up into like families.
Yeah.
The symmetry, that should be the same, but just working out what the symmetries of particular lattices would be, that's what would be.
Yes, and of course there's a lot of lattices. A lot more lattices. Yeah. Excuse me.
Any further questions or comments? Oh, no, there's time to
Okay.
lecture.
You're welcome.